All right, hello. So we're going to start off with fractions, and before we even really get into doing mathematics with fractions, adding them, subtracting them, multiplying, all that, we kind of just have to bust out a lot of vocabulary words, just so you know what all this stuff is, so I can just refer to it moving forward. And you've probably seen a lot of these terms before. So when we take a number and we write it as a product of factors, of its factors, that action is called factoring the number. So if I say something simple like 6 is 2 times 3, I have factored 6 into 2 and 3. So factor is both a noun and a verb, right? So for example, I happen to know that 60 is 3 times 4 times 5. What am I going to do with that knowledge? Nothing. That's just an example of factoring. So that was the act of factoring, and the 3 and the 4 and the 5 are factors. Another definition, the natural numbers are just the counting numbers. I think you kind of know what I mean when I say factor a number, but you can't factor a number that's like a fraction or a negative number or something like that. So we won't. And really for the rest of this discussion, when I say number, I probably just mean natural numbers. So just the positive non-zero integers, 1, 2, 3, 4, 5, up to forever. Another definition, like I said, a lot of definitions, a lot of vocabulary right off the bat here. A natural number is called a prime number if its only factors are 1 and itself. So prime numbers are often called the building blocks of the natural numbers. They can't be broken down any further. I can't ask you to factor a prime number because there aren't any. All right, and a number that you can factor, so that's not prime, is called composite. So the only two kinds of natural numbers are prime numbers and composite numbers, except the number 1, which is technically not prime. Okay, so the prime numbers are very famous in mathematics, and they're also very mysterious. Here are the first couple, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Everybody agree that you can't find a factor of any of those numbers except itself, right? Every number is 1 times itself. But those are just the first few. They stretch out to infinity. Notice one more thing right off the bat, that they're all odd except for 2. So think about why an even number wouldn't be prime, except for 2. So 2 can't be broken down any further. The rest of them are all odd, but of course not every number and not every odd number is prime. 9's not prime, 15's not prime. Here's what we really want to do with factorization. When we take a composite number and we write it as the product of all of its prime factors, what that act is called finding the number's prime factorization. So really, when we did 60 is 3 times 4 times 5, that's not a prime factorization. That's not complete. And that's really, like I said, what we're going to do with this for right now, what we're going to do with factoring numbers. Okay, so let's do an example. Yay, we finally get to do some math. We're going to bust out the prime factorization of the number 300. And there are multiple ways to do this. Once you get better at it, you can almost do it, not really in your head, but just by listing them out. But a more popular and more kind of methodical way of doing it is with something called a factor tree. So here's what a factor tree is. And this always works. And in fact, this is the way you should do it, at least for right now. So you start with a number and then you make 2 branches of your tree. And at the end of those branches, you can put any 2 factors of 300. So really, any 2 that come to mind. I think for most people, that's probably 3 and 100, right? 300 is 3 times 100. So there's your first 2 branches. Now this branch ends in a 3, and 3 is a prime number. So you stop. This branch is done. Now, if a branch is not a prime number, you just do the same exact thing you just did again. So this is one of those processes that you just keep doing it until you can't do it anymore. So pick 2 factors of 100, your favorite 2 factors. It doesn't matter. I'm going to use 25 and 4. You could use 50 and 2. You would end up with the same result no matter what. So that's why I say just pick whichever ones come to mind. All right, so neither of those numbers are prime, so we keep going with those. The only factors of 25 are 5 and 5. Those are prime. 5 is a prime number. Now, there's 2 of them, but that's okay. So we're done there. And then the factors of 4 are 2 and 2. And 2 is the only even prime. So we're done there as well. So that's it. So the prime factorization of 300 consists of a 3, 2 5s, and 2 2s. And I would like it if you wrote them in order. So when we say find 300's prime factorization, we mean write 300 equals something times something times something times something, with all those somethings being prime. So I'm going to write it as 2 times 2 times 3 times 5 times 5. It wouldn't technically be wrong if you didn't write them in order like that, but I like when everybody kind of has the same answer, and it just seems more intuitive, more like, I don't know, specific like this. When we say that officially is the prime factorization of the number 300. So it's easy to check too. You can almost do it in your head. 2 times 2 is 4, times 3 is 12, times 5 is 60, times 5 is 300, or just use a calculator, right? And then it can't be broken down any further. So there's no other way to factor 300 into primes. That's it. That's it, broken up into its like distinct building block kind of components. More definitions. Multiple of a number, a natural number, is the product of that number and any other number. All the stuff we're talking about right now only applies to natural numbers. So it's not redundant in me to say that, but I don't need to say it. So that's pretty simple. So it's easy to list out multiples of certain numbers. The multiples of 3 are 3, 6, 12, 15, 18, so on and so on and so on, right? 660 is a multiple of 3. Let's see, the multiples of 5 are 5, 10, 15, 20, 25, 30, 35, ... Obviously, they go on until infinity. And the multiples of 5 are nice because they all end in either a 5 or a 0. Okay, what is the point? We want to talk about common multiples of 2 numbers, or even more than 2 numbers, 3 or 4 numbers. And just looking at the 2 lists we just made, it's very easy to see that 15 appears on both lists, and well, 30 actually doesn't appear on the first list, but still agree with me that 30 is a multiple of 3. I think that should be obvious. So 15 and 30 are 2 multiples of both 3 and 5. So they're common multiples, right? 15 and 30 are common multiples of the numbers 3 and 5 because they're multiples of both. And the one we actually care about is 15. 15 is what's called the least common multiple. I think just from the word, it's pretty obvious what that means. But here's a definition anyways. The least common multiple of 2 or more numbers is the smallest number that is a multiple of each of the numbers. So it doesn't have to just be 2. It could be 3 or 4. You're going to want to use that abbreviation LCM. You don't want to write out the words least common multiple 100 times. Mathematicians are notoriously lazy, so we love abbreviations. So from here on out, when I say LCM, you're going to know what I mean. We're interested in being able to find the least common multiple of 2 numbers or more. So we could always do the thing where we just list out all the multiples. So for 3 and 5, it wouldn't have been that hard to just say, okay, 3, 6, 9, 12, 15, and then for 5, okay, 5, 10, 15, bam, there it is, 15. It's in both lists, so that must be it. Or in that case, you could actually just multiply 3 times 5. That's not always going to be the case, though. And either way, that's not a very rigorous mathematical way to do that. And it's not really going to work with bigger numbers. If I asked you for the least common multiple of 99 and 312 or something, you wouldn't want to just start listing out the multiples of those numbers. So we have a first kind of tricky process of actually doing something with math. Because like I said, we want to be able to do this no matter what. All right, here it is. We're going to find the least common multiple of 18 and 63, right? You don't want to just go listing out all the multiples of 63 because they're big. And you still have to check if they were multiples of 18 too. It's a 3-step process. Step 1 is to take both of those numbers and write them as a product of prime factors. So we know how to do that. So find the prime factorization of 18 and 63. I'm not going to make the tree. I think you should be able to do that. So 18 is, well, 18 is 2 times 9, which is 2 times 3 times 3. And 63 is 7 times 9, which is 3 times 3 times 7. Okay. Step 2. Step 2 is kind of like 2 steps in its own. You're going to list any common factors. So in other words, the 3 and the 3 are the common factors. And I said that right. You do want both of the 3's. So list anything those two numbers have in common, whether or not it's a repeated factor or not. Okay, so the only thing they have in common is a 3 and a 3. So list that, and then list whatever you didn't list in that. So we also have a 2 and a 7 in there. Right, so literally just make a list, like a comma separated list. So 3 and 3, and then the things, whatever's left over, whatever wasn't common factor, which is a 2 and a 7. And here's step 3. Take step 2, take everything that you listed in both your lists and multiply them all together. So we're going to do 3 times 3 times 2 times 7. Now, you could do that in order as well. If that looks funny to you, great. You know that you can multiply numbers in any order you want, though, so you're still going to get the same product. So 3 times 3 times 2 times 7 is 126. And that's it. That is the least common multiple of 18 and 63. It's easy to check that that's a multiple of 18 and a multiple of 63. Just divide it by both numbers and make sure it comes out even. Not even, but make sure it comes out to be a natural number. As far as checking that it's the least common multiple, well, you just have to be good at this. So, right, that's what the process is for. All right, so that works no matter what. No matter how big the numbers are, even if they don't have any common factors, or if they have a ton of them, it doesn't matter. That's an algebraic process that'll work no matter what. It even works with algebra, like if you have x's and stuff in your numbers, which obviously we're not there yet. And now we finally get to talk about fractions. So you know what a fraction is, just some more vocabulary terms. The top number is called the numerator, and the bottom number is called the denominator. So that fraction is 5/8. Fractions so if we have two fractions that represent the same part of a whole, we call those equivalent fractions. Really, they're equal. So if I say something like 1/2 and 2/4, really those two quantities, those two numbers are in fact equal to each other. Since we're specifically talking about fractions, we're going to use the word equivalent for now. So let's see what I mean. So for example, 2/3 and 8/12 are equivalent. Again, really they are the same number, but they represent the same part of a whole. So if you had, we always use the pizza metaphor when we talk about fractions. If you sliced your pizza into thirds and you took 2 of those, or you sliced your pizza into 12ths and took 8 pieces, you would have the same exact amount of pizza, just chopped up differently. So I think you've seen this, but it's important to know how to get from one point to the other. So to get from the 2 to the 8, you multiply by 4, and to get from the 3 to the 12, you multiply by 4. In general, that's how you're going to find equivalent fractions. You're going to multiply the numerator and denominator by the same whole number. Okay, and algebraically, that's the rule. If you have A over B, that's the same exact thing as A times C over B times C, where C is another whole number. You wouldn't do it with where C was some other type of number. So the reason you can do that is because if you think about C over C, a number over itself is always just 1. So if you're multiplying the numerator by 1 and the denominator by 1, you're not really changing the quantity. You're just writing it in a different way. Example. Write 2/3 as an equivalent fraction with denominator 15. All right, so this is not difficult. You have to figure out how to get the 3 to be a 15. And when we say get, I mean, what do I have to multiply the 3 by to get it to be a 15? Okay, that number is 5. So even if you weren't thinking about it like this, you just did 15 divided by 3 in your head, right? And got 5. So I can go ahead and multiply the 3 by 5 to get 15 as long as I do the same thing to the numerator. So 2 times 5 is 10. Right, so that's like the key number that gets us from 2/3 to whatever 15ths. So do the same thing to the numerator and the denominator. That's always okay. As far as multiplying, that's always okay. And you get 10/15ths. So, however you're picturing it, if you're picturing something sliced into 15 pieces and you take 10 of those, that's the same thing as 2/3 of the whole thing, visually and mathematically and in every other way. Right, so that should make sense to you. And 10/15ths to look at should look a little off to you because it's not what we call in like lowest terms. It's still useful to us, but it's a good instinct if it looks a little off because it can be simplified to 2/3. Here's really why we're spending time with this. And you probably know that when you add two fractions, you can only do that if they have the same denominator. So we're not even quite there yet. But if we're going to add two fractions that don't have the same denominator, we have to make them have the same denominator. So to do that, we need the least common multiple of the denominators, which is its own thing, so it gets its own term. It's called the least common denominator. Okay, the least common multiple of the denominators is called the least common denominator. So let's do one. Let's write 9/20ths and 11/16ths with the least common denominator. Okay, so we have 20 and 16, and you probably don't know off the top of your head what the least common multiple of 20 and 16 is. I don't think you probably do. I wouldn't. Okay, so you just ignore the numerators in this first step. The numerators don't do anything yet. So we know the process for finding least common multiples. We're going to find the prime factorization of 20 and 16. All right, the prime factorization of 20 is 2 times 2 times 5. So however you did that, you might be able to do that just in your head. Say, okay, 20 is 4 times 5, 5 is prime, 4 is 2 times 2. Boom, there you go. I don't know. Or you can use a simple little factor tree. And then 16 is actually 2 times 2 times 2 times 2. So 16 really only has one factor. It's just repeated 4 times. 16 is 2 to the 4th power, if you know about powers. Okay, so really the two factors we have in common now are 2 2's. So they each have two factors of 2. So those are our common factors. And then the leftover factors are the 2 and the 2 from 16 and the 5. So we don't need 6 2's. We only need 4 2's. Any multiple of 16 is going to have 4 factors of 2 in it. So the 20 already has 2 factors of 2, but we don't need those again. We just need the one that the 16 doesn't have, which is the 5. Okay, so the least common multiple is 2 times 2 times 2 times 2 times 5, which is 80. And you might just be able to just start going through the multiples of 20 and say, okay, is 20 a multiple of 16? No. Is 40 a multiple of 16? No. Is 60 a multiple of 16? No. Is 80 a multiple of 16? Yes, actually. All right, and then we have to transform these fractions into being having a denominator of 80. So now you got to just do a little, I guess, I don't know if it's mental math or what, but to get from a 20 to an 80, you multiply by 4, because 80 divided by 20 is 4. And to get from a 16 to an 80, you had to multiply by 5, because 80 divided by 16 is 5. So we're going to have to do a different move to each of these fractions. 9 over 20, we're going to have to multiply that by 4 over 4. And then the 11/16ths, we're going to have to multiply that by 5 over 5. Then we will have the same denominator, which is 80. We just don't know what the numerators are yet. All right, so 9 times 4 is 36. So 9/20ths is 36/80ths. And then 11 times 5 is 55. So 11/16ths is going to be 55/80ths. Like so. More vocab for you. A fraction is in what we call lowest terms if the numerator and denominator share no common factors. So like 9/20ths and 11/16ths that we just saw, those are both in lowest terms. 36/80ths and 55/80ths are not in lowest terms. So now we're kind of going backwards from what we just did, which is taking something that does have common factors and breaking it down so that it doesn't anymore. And by the same exact rationale that we can multiply the numerator and the denominator by the same whole number, we can divide the numerator and the denominator by the same whole number. That's completely legal to do. You won't actually be changing the fraction. You'll be finding an equivalent fraction that is simpler and better. So at the end of the day, we always want to leave fractions in lowest terms, basically. Like your final answer to pretty much every problem on, the test on this or something should be a fraction in lowest terms. Okay, so to do this, there's a couple different ways to do it. And if you're kind of used to doing it with like the slash technique where you just keep finding common factors and taking them out until you can't do that anymore, great. I'm not big on telling people how to do something if you already know how to do it. So as long as you're getting the right answers, ignore me sometimes. But a way to always do this, like let's say the numbers were big and they had a lot of factors, is you can just find the prime factorization of the numerator and the denominator and then cancel everything out at once. Like that. Okay, so I'm not doing the factor tree. We've already done that. So however you're getting to these prime factorizations. So 36 is 9 times 4, which is 2 times 2 times 3 times 3. And then 81 actually only has factors of 3. So 81 is 9 times 9. You probably knew that. And 9 is 3 times 3. Right, so now you're welcome to take a little pen and just start slashing stuff out. There's nothing wrong with that. So when the word cancel doesn't really mean anything in mathematics, we still use it though. What you're really doing is you're dividing. So you can divide the top and the bottom by 2 3s, right? Or you could have just started here and divided the top and the bottom by 9, and we would have got to the same place as we would have anyways, right? So what's left over is 2 times 2 over 3 times 3, which is 4/9. But you see what I mean? If it's faster for you in this case to just say, hey, 36 and 81 have a common factor of 9, that would in fact be called the greatest common factor of 36 and 81, the GCF. And if you see that right off the bat and just divide top and bottom by 9 and get 4/9, great, good for you, right? I'm not going to make you do it this way, because in fact, that way is even faster. Okay, this way just works no matter what. Moving on. Any number. No, don't like that. Don't like you. All right. Right, that means 5 divided by 16, not the other way around. It would be very easy to think that this means 16 divided by 5, but it doesn't. So however you have to remember it, if you did it the other way, you get an answer that hopefully wouldn't make any sense. Okay, so this means 5 divided by 16. So, okay, here we go. We love long division. We know how to do it. You say 16 doesn't go into 5, so you add a decimal place, and then you consider the number 50. So 5 is 5.0, right? Okay, so 16 does go into 50, and you think for a second, you say, okay, 16 divided by, 50 divided by 16 is 3 point something. So 16 times 3 is 48. So, right, you want the biggest multiple of 16 that is less than 50. And then remember to line up your decimal places. So this is a 0.3. I'm still getting used to this pen here. Then you multiply. 16 times 3 is 48. All right, and then you do what? You subtract. So 50 minus 48 is 2. And then 16 doesn't go into 2, but you're going to go ahead and bring down the next digit. And since our dividend is 5, we're just going to keep bringing down a 0. Okay, and then you just keep repeating that until you don't get a remainder anymore. And that'll happen soon. 16 goes into 21 times. So this is going to be a 1. My dot disappeared again. 1 times 16 is 16. You subtract again, you get 4. We're going to bring down another 0. I don't want to do the whole big arrow thing because it'd get messier. So that 0 came from there. Now we're going to need a little bit more of a divider bar here. 13 goes into 40, I think only 2 times because, I'm sorry, 16 goes into 40 2 times because 16 times 2 is 32. So the 32 goes here. Subtract again, 40 minus 32 is 8. Once again, we have to borrow a place from up here, bring it down, 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 80. And we actually just did an example very recently where we discovered that 80 was a multiple of 16. 16 times 5 is in fact 80. So you just do 16 times 5, and remember this is nice because this is the part where you can stop. So you can stop now, you can be real thorough and say, okay, 16 times 5 is 80. So you bring the 80 down again, and then when you subtract, finally you get just a no remainder. So a remainder of 0. Okay, so it's 0.3125. Now that's very easy to check for right now. You can't use a calculator on this next exam, but for right now, go ahead and literally just do 5 over 16 in your calculator. You don't have to do anything else. It will convert it to a decimal for you. I think that's what you mean. So that means 0.3125. All right, so you wouldn't know that off the top of your head. Unfortunately, the way to do it is like that, long division. Here's another example that I'm not going to do. So sometimes when it's something that's, maybe a little bit more of a process, I'll just make up another example and say, you do it. These are easy to check, but if you want to make sure you can do it now, just pause this video, do 5/12, do the long division, right? 5 divided by 12, and then just check it using your calculator. Repeating decimals. So something, just for example, like 0.416 with a little bar over the 6 means 0.416 repeating. That's how you say that out loud. And what the little bar over the 6 means is that you just keep getting that same digit, 0.4166666, and then the dot, dot, dot. So really, this means the same thing as this, just this is a much more concise way to write it. Because repeating digits in a decimal is something that comes up a lot. So that's what the little bar means. The little bar means if, you tried to do the long division, you would just remember you just keep getting the 6 over and over again. Right, so to write a decimal as a fraction, so let's do what we just did, only backwards, it's easier. This is actually a lot easier. Although you can't really use your calculator to cheat this one as easily. So just figure out the last digit in the decimal, what place value that represents, and then you can really just write it as a fraction immediately, but then you may have to reduce it. When I say reduce, I mean write in lowest terms. Reduce doesn't really mean a lot in math either, but I think you get what I mean. Okay, so let's do it. You may not know off the top of your head what 0.375 is as a fraction, so let's do it. So you just identify, okay, what does that mean? What does 0.375 really mean? Well, this is the right tenths place, hundredths place, thousandths place. So 0.375 really means 375 over 1,000. And there it is as a fraction. So you almost didn't even really do any math. You just knew what 0.375 meant. So if I didn't say in lowest terms you would be done, but I did say that. So now you have to write this in lowest terms. And you can tell that it's not in lowest terms because 375 and 1,000 obviously have a common factor. And they obviously have a common factor of 5. Now they might have more common factors than that, and I think they do. So let's do it the right way. Let's get their prime factorizations. However you do it, you'd probably start by dividing 375 by 5 and then going from there. All right, and you would find that 375 divided by 5 is 75, and then you'd go from there. 75 is 25 times 3, so 375 prime factorizes to 3 times 5 times 5 times 5, and then 1,000 turns out to be 2 times 2 times 2 times 5 times 5 times 5. Okay, so we have 3 factors of 5 in the numerator and 3 factors of 5 in the denominator, right? So we can get rid of them all. And that's all the common factors we have. Then it's just 3 over 2 times 2 times 2, which is 3/8. So there you go. Once again, pretty easy to check. Just do 3 divided by 8 on your calculator, and you will get 0.375. Or, you know, there's always, not always, but there's usually a faster way to do it, especially once you start doing it more and get better at it. So if you just noticed off the top of your head that 125 was a factor of 375, right? 125 times 3 is 375. And then maybe you could also reason out, oh, actually 125 times 8 is 1,000. So you could have just picked the biggest common factor. The greatest common factor of 375 and 1,000 is 125. You could have just divided numerator and denominator by that and been done faster. But that's tricky. Like if you didn't know that off the top of your head, I mean, why would you? Okay, so I just like to tell you that like the option is there, and I wouldn't dock you points for doing it that way, as long as you showed me what you did. You know what I mean? As long as I can see your work. And then finally in this section, we come to percents. So percents aren't the same as fractions or decimals, really. They're their own kind of thing. And you know that because they specifically refer to being something out of 100. 100% is everything. So let's talk about that. Right, so there's your definition. Just think like Latin stuff. Cent means 100, like centennial or whatever, right? So percent literally means per 100. I mean, literally, that's what the word is. So you always know the percent's out of 100. Right, so 100% is everything. If you see something like 30 over 30%, you know that that doesn't really mean 30, it means 30 out of 100, or 3/10, right? That simplifies as 3/10, or 0.3. So 30% is the same exact thing as 0.3, right? So percents can be a little misleading because it's like you almost never really do math with percents. They're just there because, well, it's just a convenient way for us to think about certain things. All right, so if I give you a percent and you have to do some math with it, you're probably the first thing you're going to do is convert it to a decimal. So to convert a percent to a decimal, just like we just did with 30%, you divide that number by 100. You do 30 divided by 100. And you know that when you divide numbers by numbers like 100 and 1,000 and stuff, you just end up moving the decimal place, right? So you don't really literally need to go in and do 30 divided by 100. You could, but I wouldn't. Because since we use a, well, literally decimal system, deca meaning 10, it's easy to do things like multiply and divide by numbers like 100. Okay? So, for example, if I give you 27.5% and I say, give me that as a decimal instead, you're going to do 27.5 divided by 100, which all you need to do for that is take that decimal place and go just 2 places to the left. So it's 0.275. So when percents go to decimals, just think they always get smaller, right? 27.5% might seem like a big number, but it's just that much over out of 100. So it's like a little more than 1/4. So 0.275. We all know that we can have numbers that are bigger than 100%, right? You're going to give 110% in this course. So that just means there's more than everything. So like if something grew, you would say there's like 110% of what there was before. But that doesn't affect what we're doing now. If you're changing that to a percent, or I'm sorry, to a decimal, you're still just going to divide it by 100. So over goes the decimal place, and you're going to get 1.1, right? So a percent that's bigger than 100% is going to correspond with a decimal that's bigger than 1. It's a little bigger than 1. If you had 200%, that would just mean like something doubling. 200% is the same as just the number 2. Other way around, just do the opposite. So if I give you a decimal and tell you to convert it to a percent, you just go the other way. You just make it bigger by multiplying by 100. And when you know that when you multiply a number by 100, you just have to move the decimal place over the other way. So this number 1.65, this is a number that's more than 1. So if you had to convert that to a percent, you just go over 2. Sorry, you're backwards for me. Go over 2, and that would be 165%. And then always write the percent symbol when you mean a percent. It should never be unclear whether what you're looking at is a percent or not. Normal numbers like 1.65 don't need a unit. So when you see 1.65, don't think, is that a number or a percent? Well, there's no percent sign, so it's a number. But you shouldn't just write, like your answer here shouldn't just be 165, right? So if you didn't put the percent symbol here, like I would take a point off, okay? So it's important to be clear. So there's a very tiny decimal. It's still going to get bigger, but it's going to be a pretty small percent as well. So the same deal, just move the decimal place over to the right, and you get 0.2%. Okay, so 0.2% is tiny. It's less than 1%. Okay, and that is, yeah, that's that, okay? Fractions, decimals, and percents, we're going to be using those for pretty much everything we do in this course. So just be good at them. Thank you.